Hi everyone, so today we're going to look at integration from A level and we're going to get started going through some of the key ideas at the end of the course.
Okay, here we go.
So to start with, we're going to just do a simple basic reminder of integration. So integrating this, remember we add 1 to the power and then divide by the new power. The first thing I'm going to do is rewrite this. Okay, and now carry out the integration. And now tidy it up. Okay, and there we go. Right, the next one, I'm going to just look at a bit of integration by recognition. So this is basically looking at what we've got and thinking, well, what would differentiate to give me this? And this really is kind of treatment of integration as the reverse process of differentiation. So I know that sine differentiates to cos, but there's kind of a bit of chain rule going on here as well. So if I make the guess that it's got to be something to do with sine 6x, okay? Because I know sine 6x differentiates to 6 cos 6x. So if I actually differentiate that guess and get 6 cos 6x, that guess is actually out by a factor of 6. So all I do is I find an adjustment factor and I say, well, if it was a sixth of the size, then that would work. And that actually is my answer. So basically I know it's something to do with sine 6x, but if I take that as a guess and then I differentiate my guess, and so my adjustment factor is times by a sixth to my original guess. And that's it, that's our answer. Similar way, e to the 5x, I know e to the x differentiates to e to the x. So my guess is actually going to be e to the 5x because I know that's got to be part of the answer. And if I differentiate that guess in a similar way, I get, which is 5 times 2 big. So my answer is actually a fifth of that plus c. So when I'm saying guess, it's not a complete guess. I know the key part of the function that the answer should involve, and then I'm just adjusting it accordingly. Okay, right, let's move on. So a couple of other examples of recognition. I'm going to rewrite this one. Okay, so 5 plus 4x to the half. Now, if I think of this again, this is like a chain rule question. So I know that in the chain rule even, the power does drop by 1 when I differentiate it. So this seems to be the key part of the question. So I'm going to take my guess as that bracket raised to a power increased by 1. So I'm going to guess it has something to do with 5 plus 4x, not to the half, but to the 3 over 2. Because I know when I apply chain rule to that, I get the 5 plus 4x to the half that I want, plus some other numbers and bits coming out. So I can just, again, find an adjustment factor and fix that accordingly. So let's differentiate my guess. So again, this is chain rule, and it would give us times by the derivative of the inside with respect to x, which is 4. So it would give me 12 over 2, which is 6, which is nearly what I want. It's just 6 times 2 big. So what I'm going to do is a sixth of my guess. So my answer will be a sixth, 5 plus 4x to the 3 over 2, because that was my guess, but it came out 6 times 2 big, plus c. Okay, and remember, don't forget you can always actually differentiate it and check it does get you there. Right, very similar, this last one. So I'm going to rewrite this as the integral. And again, I'm going to do the guess thing, and I'm going to go add 1 to the power of this bracket here, okay? So I'm going to guess, and it is an educated guess, it's, you know, it should get you most of the way there. It's something to do with this to the power of minus 3, because remember, I've added 1 to minus 4. Now let's differentiate that guess. Again, chain rule, and then make the comparison of how far away we are from what we want. That's going to be minus 3, 6 plus 3x to the minus 4, multiplied by the derivative of the inside, which is 3. So I get minus 9. Okay, now we're out a little bit. I've got minus 9, but I actually want 2 lots. So the adjustment factor this time is I need to multiply by minus 2 ninths, because minus 2 ninths times minus 9 equals positive 2. So my answer is minus 2 ninths of my guess. There we go. Cool. Okay, here we go. So now we've got integration by substitution. And this is a kind of slightly more formal technique used for the same sort of questions as what we were just doing. So again, it's for kind of chain rule differentiations, getting back to them via integration. So if they give you the substitution to use, let's work through and see what happens. So what I want to do is I want to replace the x's in terms of u, but I also need to replace dx because that means with respect to x. And I can't integrate a function with respect to x if it's all in terms of u. So I need to integrate in terms of u. Let's use that substitution. So I'm going to get x times, and then u is being replaced. So 1 minus 3x cubed would actually be u cubed dx. The problem here is we've still got a dx and we've still got an x. So hopefully you can see I've replaced 1 minus 3x, that bracket, with u. So it's u cubed. I need to just sort out what x would be in terms of u. So if I rearrange this, okay, x is equal to 1 minus u over 3. So I can replace that. So we're getting there, but we've still got this dx, and we want to sort that out. So a couple of ways I could do this. I know that u equals 1 minus 3x. So if I differentiate that, du dx is equal to minus 3. And now if I rearrange that and make dx the subject, du over minus 3 equals dx by timesing up by dx and divided by minus 3. So I can replace dx with this. Okay, so I get Now, at this stage of integration, I would probably factor out -1/9 because I don't like the 1 over -9. And then I can just deal with the fact that I'm integrating this scenario here, because any sort of factors or constants can be brought out to the front of the integral. So this will give me -1/9, the integral of u cubed minus u to the 4 with respect to u. Now I can carry out the integration because everything's in terms of u and I'm integrating in terms of u. So I get -1/9, and then what this would become would be, and if I re-expand that, and then actually what I can do is to put u back in terms of x. And then one final technique I'm just going to show you, and that sometimes comes in handy, is writing this in a fully factorized way. So obviously -1/9 has already been taken out, but there is also a common factor of 1 minus 3x to the 4, because that goes into both bits. And to the first bit, it goes in 1 over 4 times, and then the second bit, it goes in minus another 1 minus 3x over 5 times. And again, if you don't like having fractions in there, because I think, again, it's a little bit annoying having 4 and 5, you can take out a factor of a quarter and a factor of a fifth out. And to do that in one go, you could actually take a factor of a 20th out. So this would be the same as a 20th, and 1 out of 4 in 20ths would be 5 20ths. And this would be the same as 4 lots of this. So that is essentially 5 lots of the 20th is a quarter, and 4 lots of the 20th is a fifth of this. So now I've factored out the 20th, this can kind of get absorbed in this factor here, and I can tidy this up again as the following. This can actually be expanded and tidied up as well. And there we go. So at this stage, you'd actually done the integration. Then here it's putting it back in terms of x. And then the tricky bit was actually factorizing it all, taking out the highest common factor of 1 minus 3x to the 4, and then dealing with the fraction. The integration is actually completed by here. Okay, right, let's look at another example. So here we go. We're told to use the substitution u squared equals x plus 1. I'm just going to write a couple of little key things here. So if u squared equals x plus 1, then u squared minus 1 equals x. The other thing we can do is find dx du, because I think it's going to be easier to do it this way around. The derivative of x with respect to u is 2u. Okay, let's sum all that in over here. So x squared would be the same as u squared minus 1 squared. And root x plus 1 would be the square root of u squared, which would be u. Dx is equal to 2u du. So I can replace that. And then I can carry out the integration after tidying this up. Then actually integrating that. Now remember, u is equal to x plus 1 to the half, or square rooted, so I can put that back in. And again, I could factor out the highest common factor here, which would be u plus 1 to the 3 over 2. It would be 2/7. Right, so it gives us this. Okay, so that is the integration. Now again, just taking the time to show you how this tidies up. The highest common factor is x plus 1, 3 over 2. There's 2/7 of that, and then I need another 4 more. 4 over 2, more lots of that, which is 2 lots of it. So x plus 1 squared. Here, minus 4/5, and that would be, and that is the bracket already that's been factored out. And in terms of the fractions, I think the lowest common multiple, so a multiple of 3, 5, and 7, let's times them all together. They're relatively prime. So 15 times 7, 105. So we take out 1 for now. And how many times is 7 going to 105? 15 times 2 would be 30. How many times is 5 going to 105? 21 times. 21 times 4. And then 2/3 plus 70. Now, if I can still take out a factor of 2, and you could expand and tidy up even further, but I'm going to leave it there. Okay, let's keep going. Right, this one. So we're told x is equal to 2 sine u. Let's sub that in. And then let's also think about dx. So dx du, so I can sub that in place for dx. 4 is a common factor, and that gives us 1 minus sine squared u, 2 cos u du, which equals the integral between 3 and 1. Now these are currently x bounds, but we can deal with that in a minute. I'll just leave them as they are. This is 1 over. Now root 4 times 1 minus sine squared u. 1 minus sine squared u from the identity is actually cos squared u. So that's 1 over root 4 cos squared u times 2 cos u du. And hopefully we're noticing this tidies up quite nicely, because root 4 cos squared u is 2 cos u. So 2 cos u over 2 cos u is just 1, okay? So I am essentially integrating 1 with respect to u. And if I do that, I get u. And then I can, obviously this is with x bounds, and I could change them to u bounds, or I could just put that back in. Right, I hope that was useful. Integration is a massive topic, it is tricky. So well done with that. Keep working away at it. There's so many resources you can use to practice this, so make sure you do.